Now that we've talked about the motion of charges, we need to think about a slightly more complicated object, which is going to be a dipole. We're not really going to do, for instance, the motion of a charged plane in an externally created electric field. Later on when we get to magnets, magnetic fields, we will talk about wires and some other things. But for right now, we're just going to focus on point charges in electric fields and dipoles in electric fields. So the dipole is a little more complicated because we have to worry about two pieces. We have to worry about the negative piece and the positive piece. And to remind you, the definition of a dipole is that you have an equal in magnitude negative and positive charge that are separated by a very small distance. Now, if it is in a uniform electric field, there's actually no net force on the dipole. Why would that be? We can break this into two parts. We can just think about the positive part and the negative part separately. The force on the positive part is given by positive Q times your electric field vector, and the force on the negative part is given by negative Q times your electric field vector. So if this is uniform, that means that these two electric fields must be equal. So if they are equal, that means that we have positive QE plus minus QE. That's definitely equal to 0. So a dipole in an electric field, a uniform electric field, is going to be in equilibrium. It has 0 net force on it. Now, what's a little tricky to think through, and we're not going to go into detail in this, but if you place your insulator in an external electric field, you induce dipoles, right? There's permanent dipoles like a water molecule, and then there's induced dipoles. Note that once you have induced the dipole, you then are in equilibrium. So it's like you start with a non-polarized insulating material. You put it in this external electric field. At that case, there are forces that are just pulling the dipole apart, but then it stops when it reaches this equilibrium condition. So we'll talk about in a few slides the fact that we saw those attractive forces, but right now this is different. When we did experiments, we saw attractive forces between neutral and charged objects due to polarization and induced dipoles. That was not a uniform field. So part of why I'm stressing the uniform field here is that what we're about to talk about is not what we normally observe because we don't normally observe uniform fields. So force was pretty simple. We got to say that it was 0. Torque is going to be a little more complicated. Part of what makes torque more complicated as well is that for many of us it's a more challenging topic. It was something we covered in mechanics, but usually it's not a topic students feel that they have great mastery of, and we spend a lot less time on it than we do basic forces. So think about it this way, that if we have our dipole as before, just aligned with the electric field, we said it's in equilibrium, net force is 0. But imagine that it's rotated a little bit. We still have our forces in the same direction, right? If you look at these two forces, they have the same magnitude and the direction. That hasn't changed. But now there's this angle here, and you can think of there being a pivot point. So to briefly remind you, torque is going to depend on a force, where it acts, and which direction it is. So we have to have an axis of rotation, which we typically put in the center. And in this case, we see that the forces are not acting at the center. Lever arm is then the perpendicular distance from where the force acts to the pivot point. So the lever arm is basically this distance. So we see that we're going to cause a torque. We're basically pulling on it and it's going to rotate. But not only does this force create a torque, but so does this one. But they're actually making it rotate in the same way. So before we even get to the math, hopefully how you can think about it is that if it was just rotating around this point, that's your pivot, and this force would actually make it rotate this way, pulling on it. This force is also pulling on it and would also make it rotate that way. So these two torques, right, if we think about torque 1 over here and torque 2 over here, those two torques are actually going to add. They're not going to cancel, even though the forces cancel. So in this situation, it's still true that the net force is 0, but the net torque is not. And remember that you cannot find net torque by first finding the net force and then finding the torque, you actually have to find your individual torques first and then add them up. So what does this look like? So we have two torques, remember, so one from the negative, one from the positive. They actually have the same moment arm, which is this, and then they have the same magnitude of force, which is just this. So we get to multiply 2 times our lever arm times the force. And the force is again given by the charge that's here and the electric field. And remember that we said it was uniform everywhere, so this is specific to a uniform field. The moment arm then is that perpendicular distance, so it relates to the sine of this angle, because that's basically saying the opposite side of your triangle. And then 1/2 s, because your hypotenuse here is basically s over 2, not just the whole s. So 2 comes from having both a negative and a positive charge, each contributing to the torque equally. Our lever arm is 1/2 s times sine theta. QE is your force. So then remember that we can actually write Q, our charge, times S, the separation, as P. So P in this case is not momentum. This is your dipole moment, which we introduced before when we introduced the idea of dipoles. So we can actually write, and this is a slightly general result. So this is true for any dipole in a uniform electric field. We can write it as actually the dipole moment times the electric field that it's in, which is uniform, times the angle that the dipole makes with the field. Now, one approach to working with torques is actually using cross products, which is a specific vector manipulation. Now, I know for some of you, you've had math classes or possibly past physics classes that have covered cross products, but it's typically something that we don't talk about when we cover torque in Physics 202. So this is a different way of writing the same thing if you actually know what cross products are. If you don't know what cross products are, don't worry about it. This isn't just multiplication, it is in fact something special. So this is kind of the best thing to think about unless you're already an expert on cross products. So again, we see for a uniform field that we get 0 net force, but we do get a torque as long as it's not aligned with the field. Then we can say, well, what happens in non-uniform fields? Now, again, this is interesting because this was more the situation we had when we did experiments. So if I charge a plastic rod and I bring it near a neutral piece of styrofoam, I don't have a uniform field. I have a non-uniform field, and it looks kind of like this. So this actually will give us that attractive force that you might expect to be there. And again, it's because it's non-uniform. So if I have my point charge, I know that my electric field gets weaker as you get farther away. So that means that my force on the negative charge is much bigger than the force on my positive charge. Simply because my positive charge, okay, much is maybe an exaggeration, but my positive charge is farther away. So there is a net force and it's attractive. Now, this could be for an induced dipole or a permanent dipole. If this was a minus sign, then this dipole would either flip around, physically rotate, or if it was simply an induced dipole, it would switch which one. So you always get an attractive force simply because the repulsive force is small and away, the attractive force is large and towards. Now, what's interesting is that if we think about allowing both of our objects to move, and in this case we have, say, a water molecule and a sodium ion, that we have a net force on the dipole, again due to the difference in position, but we also have a net force on this ion. And the reason for that is that it is seeing two point charges in this dipole, and it is closer to the negative one. So you could actually draw those field lines for this situation. Remember that we've previously calculated the fields from dipoles, and you could calculate what this distance is. But in fact, you see that both of these are experiencing an attractive force, and as this line shows, this is actually a Newton's third law pair, that this is two objects that are interacting with each other via the electric forces, so the magnitude of the force on one is equal to the magnitude of the force on others, but they're in opposite directions and they act on two different objects. So we're not really going to do more of a calculation than that. It really depends on how your field is non-uniform, but just remember that you do get attractive forces.